I want to show you another method for finding the volume of a solid of revolution. It's called the washer method. First of all, when we're talking about a washer, that is a disc that has a hole running through the middle of it. To find its volume, we do that in the same way we do every other cylindrical solid, and that is by finding the area of the base and multiplying it by the height. The thing is, in our washer, we do have a height or the depth of the washer, but its base has a unique shape. It's this. It's a circle with a hole cut out of the center. Describing that shape as a circle with a circular hole taken out of it helps us to define the area of the base and helps us to calculate it. Because when we think about our shape as being a large circle, well, the larger circle has a certain radius, and from that we're going to take out a smaller circle. So we're going to subtract this smaller circle with a smaller radius. All right, that would mean that as far as the area of that base is concerned, we would first find the area of the larger circle, which is pi r squared, and then we'd subtract from it the area of the smaller circle, pi times little r squared. Now we can put these two ideas together and come up with a volume of a washer as being the area of the base, that pi r squared minus pi little r squared, times the height or the depth of the washer. How that washer becomes helpful for us is when we're trying to find the volume of a solid of revolution that has a hole running through the middle of it. When we take a look at the region that's being rotated around from right here, we see that we're going to have the difference of two functions. So it's this little yellow box that gets rotated around the x-axis, creating a vertical washer that looks like this. Now, since we're dealing with a vertical washer here, the depth of that washer is going to be delta x. And we need to identify our two radii. So on the outside, the larger radius, in this case, goes from here to here, and that's going to be f of x. Our smaller radius is this part that gets subtracted away, and that's going to be g of x. So the volume of our washer is going to be pi times big R squared. In this case, our big radius is f of x. And we'll subtract off pi times little r squared. In this case, our little radius is g of x. And all of that gets multiplied by the height or the depth of the washer, delta x. Now as we translate that into the volume of our solid of revolution, when we start stacking infinitely many of these washers and let delta x approach 0, we will have, just like before, a definite integral of pi times f of x squared minus pi times g of x squared, and our delta x turns into dx, and it has to go over the entire interval, in this case from here to here, which was a and b. So our integral from a to b. And this will be our method for finding the volume of a solid that has a hole going through it. So let's find the volume of the solid form by rotating the region bound by y equals square root of x and y equals x squared around the x-axis. Of course, the first thing we should do is graph it. Well, when I graph y equals square root of x, we get this sideways parabola. And with y equals x squared, that is a parabola that opens vertically like this. So the region that we're talking about is that region that's bound by both of them. So this part that's in between, and that's going to get rotated around the x-axis. So when we do that, we'll end up with a symmetrical shape down here, and everything is rotated this way. And this will be a solid that has a hole running through the entire length of the solid. That means that we'll be dealing with a washer, and these washers are going to be vertical washers that are stacked along the x-axis. Now when we have our vertical washer, the depth of that washer is going to be delta x, and we need to identify our two radii. The top radius, the big radius, is going to be our outside function. In this case, that's square root of x. Our smaller radius is going to be the inside function, right here, which is x squared. Now that I have my washer, I can set up my integral for finding the volume of our solid of revolution. It's going to be pi times the big radius, in this case square root of x squared, minus pi times the little radius, x squared, dx. The only thing we're missing are two limits of integration. So we need to go back to our graph and figure out what is the interval. To do that, we need to identify our 2 points of intersection. Well, with x squared and square root of x, it's fairly easy to see where those 2 points are. The first one is going to be at the origin, and the second one is going to be the point 1, 1, because 1 squared is 1, and the square root of 1 is 1. That's going to mean our limits of integration go from 0 to 1. Before we calculate this integral, we could probably clean it up a little bit. The square root squared is just going to be x, and the x squared is going to be x to the 4th. Now, whether you do this by hand or you use your calculator, I'll let you do that on your own, but you should end up with a result of 3 pi over 10, or about 0.942. Let's try one more. Find the volume of a solid formed by rotating the region bound by the x-axis and y equals x squared on the interval from x going from 1 to 3, rotated around the y-axis. When we graph it, y equals x squared plus 1 is a parabola with a y-intercept at 1 and a vertex at 1. So something like this. Now we want this to go from 1 to 3. That would mean from 1 over to 3. So this is our region that's going to get rotated around the y-axis, like this. So we see we'll have a hole here. And there's a different hole on top. This problem is a little bit more difficult, not just because we have a horizontal area, but because this volume can be thought of as being broken into two separate regions, where we have a top solid and a bottom solid, because this part is going to be a hole. There's a hole running all the way through this solid. So we're going to break it up into two pieces right at that point, which we said was at 1. So our region will be split here with a top region and a bottom region. First, let's think about just the top region. Since our area we're thinking of as a horizontal area, the depth of our disk is going to be delta y. And for the top region, we need to identify our outside function and our inside function. So the outside function goes out to here, which will be 3. The inside function is going to be the curve. But remember, we need to have this written in terms of y. Right now, we know that curve to be y equals x squared plus 1. So if we solve this for x, x will be plus or minus the square root of y minus 1. Since we're dealing with the right side, that's the positive square root. The bottom region is going to be calculated in a similar way. It's also thought of as a horizontal area, so we'll have this horizontal washer, and its height will be delta y. When we consider its 2 radii, the outside radius out here is going to be 3, just as it was in the last washer. But it's the inside function that's different. All right, we'll just have this vertical line, and the distance from the y-axis over to that vertical line 1 is just 1. Now we have enough to start calculating our volume, at least setting it up. So first of all, we'll have this integral of our top region rotated around, which will be pi times the large radius squared minus pi times the smaller radius squared dy. For our second solid, it's going to be pi times the larger radius squared minus pi times the smaller radius squared dy. But we still need our limits of integration. So let's take a closer look at our picture. Now earlier I said that we split our region when y was equal to 1. Now that's not exactly true. Where y equals 1 was where our parabola had its y-intercept, down here. However, where we're trying to split our region happens at this point, which is slightly above y equals 1. But it does happen when the x-coordinate is 1. So I want to look at y equals x squared plus 1 when x is 1. So that'll be at 2. This is the point 1, 2. The other point is going to be on the end of our interval, and that's when x is 3. Of course, for 3 squared plus 1, we'll end up with 10. Now we can go back to our integrals. Our first integral described the top region, so from y equals 2 up to y equals 10. And our second integral described the bottom region from y equals 0 up to y equals 2. There is a little simplifying that we can do before we get to calculating this integral. 3 squared is going to be 9 pi minus pi times y minus 1. And over here we'll have from 0 to 2 of 9 pi minus 1 pi. And it looks like 9 minus a negative 1 would be 10 pi minus pi y dy. And we'll have 0 to 2 of 8 pi dy. Once again, I'll let you calculate this on your own, either by hand or on your graphing calculator, but you should end up with 48 pi, which is about equal to 150.796. But that's how you use the washer method to find that volume when there's a hole running through the entire solid of revolution.